Hi, welcome to the third video for the earthquake engineering. In this video we're going to discuss two things. The first thing is multi-degree of freedom structures, okay? And the second thing is the response spectrum. What about multi-degree of freedom structures? As we discussed so far, we only had a single degree of freedom. So what does this mean? We had a frame with the mass, all of the mass is, lumped or, is at one level over here, okay? You just have a one-story building, okay? So the entire mass is at one level, so you did a static condensation and you only studied this mass. But now when you have a multi-story building, 2 floors, 2 stories, or 3 or 4 or 5, okay, we cannot use the same procedure that we did. Now we have the mass being divided on this floor and this floor, okay? When an earthquake is applied, okay, I have to study those two masses separately, okay? How can we do this? This is since we're going to have two masses. If we have a 40-story building, we're going to have 40 masses that I have to study each of them and the vibration and the movement, the displacement of each of one of them. So here you have the displacement of this floor, U1, as function of time. We want to find this response as well as U2 of t, okay? The displacement of the second floor, okay? How can we do this? Okay, we draw the free body diagram for each of those masses and apply displacement U1 and try to find the forces, okay, and apply the equations of equilibrium. So now let's understand this exactly as we did in structure analysis too. So the definition of a stiffness, okay, K is the force required, okay, to give a unit displacement. Now here, assume we have this two-story building. It's supported by those 3 columns here on the first floor, two columns here on the second floor, okay? And there is only a displacement on the first floor, so the columns drift like this, okay? So now the column, those columns, column 1, 2 and 3, 4 and 5, wants to move back the first story to its initial position. There will be a force that is depends on this displacement U1. Let's assume there is no U2, just U1, okay? So there will be a K1, okay? Now we're going to call this K11U1, okay? Why K11? Because this is the force at the first level, okay, due to a displacement at the first level. That's why we're calling it K11, okay? So K11 comes from the contribution. All the 5 columns want to push back the first story or the first floor here back to its initial position, okay? So K11 comes from the first, so it's going to be equal to K1 of the first column, which we mentioned before. It's 12EI divided by L cubed if it's a rigid floor, or 3EI divided by L cubed if we have a pinned end columns. And K2 and K3, K4 and K5, all 5 columns want to move that back. On the other side, if this is moved to U1, okay, there will be a kind of a force here on the top floor, okay, to hold it back so that it doesn't move, okay? We are saying here U2 is 0. So actually the second floor wants to move with the same displacement U1, but actually there is a force, okay, kind of a force, okay? So those two forces will be opposite to each other. So K11 U1 wants to move this back, but actually there is a force that wants to move this forward. So we're going to call this K21. This is the force due to a displacement. It's the force at the second floor. That's why I'm naming it K2, due to a displacement at the first floor. So K21 U1, okay? How many columns want to push this floor forward? It's K4 and K5 here, just those 2 columns. So K21 is opposite. It's opposite in direction, so it's negative K4 plus K5. Now let's assume the other way, okay? U1 is 0 and U2 is the only thing that happens. So if there is only U2 over here, those 2 columns, K4 and K5, wants to move that back. So K22 will be K4 plus K5. The K12, there will be a force over here because this one wants to move, but it's going to be opposite in direction to this force. Those 2 forces will be equal but opposite, okay? So K12 is negative K4 plus K5, so there is a negative 5 over here. So K22 is K12, but it's with a negative sign in that case over here, Okay, so now what if we have both u1 and u2 applied on a structure all together? We're gonna have to add those together, okay, and applied with a dynamic force. So here, when u is going this direction, there's going to be an inertia force in the opposite direction. So mu1 double dot. When there is u2 over here, there will be an inertia force mu2 double dot. Okay, let's write the equations of equilibrium for the forces on the first floor. So you're going to have k11 u1 mu1 double dot plus k12 u2, because you have now u1 and u2 applied all together. So the equation of equilibrium for the first floor is m1 u1 double dot plus k11 u1 plus k12 u2, and this is equal to 0. Definitely there might be also a damping factor, okay, but right now we're also starting with the undamped equation of motion, the free vibration. There is no force over here, okay. The equation of motion of the second forces, so the equilibrium of the second story over here, you have k22 u2 plus mu2 double dot and k21 u1, okay. So those has to be 0. So the equation of motion for the second floor, you have m2 u2 double dot plus k22 u2 plus k21 u1 equals 0. So now we have those two equations. Instead of leaving those two equations as just two equations like this, let's write them in a vector and matrix form. So what we have here, we have m1 multiplied in the first equation, m1 multiplied by u1 double dot. So I have m1 multiplied by u1 double dot, and there is nothing in the first equation here multiplied by u2 double dot, so I have 0 multiplied by u2 double dot. And then the second, and then over here I have k11 multiplied by u1 and k12 multiplied by u2, so I have k11 multiplied by u1 and k12 multiplied by u2, okay? Those are equal to 0. And then the second equation can be written as 0 multiplied by u1 double dot and m2 multiplied by u2 double dot and k21 multiplied by u1 and k22 multiplied by u2 equal to the vector over here, the forces that we would have if there were any forces on this side. There will be the load vector. So now, instead of having mu double dot plus ku equal p as scalar values, we actually have them here as vector or matrix form. So now it's still the same form, mu double dot plus ku equals 0, but m now is a vector, is a matrix. It's this diagonal matrix that has the masses of the first floor, the second floor, and then a vector that has u double dot, the acceleration for the displacement of the first floor, and the acceleration, a vector that has the acceleration of the first floor and the acceleration of the second floor. Also here k now is a matrix. Now this is the stiffness matrix. So how do you build the stiffness matrix? Exactly as you did in structure analysis 1, okay? So now k is not just a value, it's a matrix, okay? So definitely if you're just interested in the horizontal displacements, the only displacement that you have are u1 and u2, you can start with a very big, large stiffness matrix, and then you do static condensation until you get just u1 and u2, as we did at the start of the semester, okay? In the start of the semester, we had a single story frame, and there was actually 3 degrees of freedom, okay? We eliminated 2 by the static condensation. We only had the displacement, the horizontal displacement of the first floor. Also here, when you have a large building like this, you can go ahead and build the stiffness matrix. Maybe have u1, u2, theta 1, theta 2, theta 3, theta 4, theta 5, and then you do a static condensation to eliminate theta 1, theta 2, theta 3, theta 4, theta 5, and just have, the matrix will look just like this, okay? So the stiffness matrix like this, okay? And multiplied by the displacement, those will be equal to the forces. So if there are forces applied, they're going to be in this part. Now, instead of just having mu double dot plus ku equals 0 as one single equation, no, we have a system of 2 differential equations. When this is actually represent 2 equations like this, 1, 2, and each of those equations is a differential equation. And those 2 equations are coupled together. This equation has u1 and u2, and this equation has u1 and u2, so they are coupled together. I cannot just solve one of them independently of the other. I have a system of coupled differential equation. I cannot just use one of them to solve for u1 or u2 and then substitute that, or find u2 from the other equation, for example. No, I have to solve them all together. It's like simultaneous equations. You need all the two equations together to enable to find how much is u1 and u2. So the equations we have is now written in a matrix form like this. Okay. So what do we want if we want to solve this? When I say we want to solve this, what do I mean by this? Simply, we need to find how much is u1. The displacement of the first floor is a function of time, and the displacement of the second floor as a function of time. Okay, so how can we do this? Exactly as we did with the single degree of freedom system. We're going to assume that u1 of t and u2 of t is equal to some constants, x1 and x2 multiplied by e bar lambda t. Okay, so x1 and x2 are constants. Okay, and x2 are constants. So how much is lambda? Okay, that satisfies this assumption. Okay, so simply substitute this assumption into this equation. We have m, this is the mass matrix, multiplied by u double dot of t. So the second derivative of this is going to be this vector x1 and x2, and then the second derivative of this is going to be lambda square e bar lambda t. So lambda square e bar lambda t plus k u. U is, I'm assuming it's x1, x2, e bar lambda t equals 0. So I can divide the entire equation with e bar lambda t, so those two terms will cancel over here. So I'm going to have here lambda square multiplied by the mass matrix multiplied by this vector x that has the two constants x1 and x2 plus k, the stiffness matrix, multiplied by this vector x equal to 0. Okay? Now if I multiply the entire equation by the inverse of this mass matrix, so m inverse multiplied by m, that will give me the unit vector, matrix. Okay, so lambda square multiplied by the unit matrix multiplied by this vector x, okay, plus m minus 1, m inverse multiplied by k, x is going to be equal to 0. Okay, m inverse multiplied by 0 is 0. Okay, so as you see here, this equation, okay, is an eigenvalue problem. Okay, or an eigenvalue equation here, where you have, what's the generalized eigenvalue equation, is where you have lambda square, a constant, multiplied by this unit vector x is equal plus, okay, some matrix over here, okay, multiplied by the same vector equal to 0. If you move this to the other side here, simply you have a vector or a matrix multiplied by a vector is equal to a constant multiplied by the same vector. Okay, so how much is that constant that would satisfy this equation? Okay, this is the eigenvalue problem. The generalized eigenvalue problem is here, instead of lambda, it's lambda multiplied by I. Okay, so actually we are after how much is lambda that would satisfy this generalized eigenvalue problem. So here I'm going to assume this as a one matrix, m inverse multiplied by k is a. So the lambda that satisfies this equation comes from this equation. The only lambdas that satisfy this equation is where the determinant of this vector matrix A, okay, which is m inverse k over here, minus this vector matrix lambda square I, the determinant has to be 0. Okay, so simply how can you do this? You want to find the determinant of A of m inverse k. Okay, so m inverse, what's, if this is m, the mass matrix is always only a diagonal matrix. You only have mass at the first floor, the second floor, while those two parts will be 0, the other diagonal here will be 0. If this is m, what's the inverse? It's going to be 1 over m and m1 and 1 over m2. Even if this is a 10-story building, there will be masses of the 10 stories on the diagonal m1, m2, m3, and the inverse of this would just be the inverse of the diagonal values. Okay, so now this is m inverse. I need to multiply m inverse by k, so I have m inverse by k is going to give me that matrix. So this will be this vector matrix over here. I want this vector matrix minus lambda square I, so that means A minus lambda square I will be, I'm just going to be subtracting lambda square from the diagonal members over here, because I is the unit matrix, which is just 1 on the diagonal and then 0 of the diagonal elements. Okay, so this matrix, the determinant of it has to be 0 in order to have a solution, okay? So the determinant of this matrix will be just the multiplication of this diagonal minus the sub multiplication of the other diagonal. So A11 minus lambda square multiplied by A22 minus lambda square minus A12 multiplied by A2 equal to 0. This will be a second, those are constants, okay? So this is a second order equation. Lambda squared is going to have two solutions. So those are the, the solutions. Lambda 1, lambda 2 that comes from the solution here of this eigenvalue problem. Okay, so since we had 2 degrees of freedom only, we had two solutions. If we had a 40-story building, we would have this equation to be 40, where the mass matrix will be 40 by 40. The k vector will be, or the k matrix will be 40 by 40. When you're going to be solving an eigenvalue problem that is 40 by 40, you're going to have 40 solutions over here, or 40 solutions for the equation over here. Okay. For any stable structure, actually lambda 1 squared and lambda 2 squared will be negative. That means that lambda 1 and lambda 2 will be an imaginary value. So lambda, the lambda 1s and lambda 2 will be an imaginary numbers like this, okay, with multiplied by some value. Imaginary number multiplied by the w, and w is going to be the square root of lambda squared, okay? Lambda, sorry. Now the solution u1, u2 will be some parameter x1, x2 multiplied by e power lambda t. But lambda, we realized that there are two lambdas, right? So the solution might be a linear combination of the two lambdas, e power lambda 1t and e power lambda 2t. So u1, u2 would be some two constant x1, 1, x2, 1 multiplied by e power negative w omega 1 it, okay? Omega is going to be, you have I here because omega is going to be an imaginary number plus some two other constant x1, 2, x2, 2 multiplied by e power I omega it. So actually here this is omega 2, this is this is 2, and this is I, and this is omega 2, okay? So as we did for the single degree of freedom, when you have this exponential functions, okay, with an imaginary power, you can, using the Euler's formulas, you can replace those with cosine and sine. So actually you have, okay, the system here oscillating with those degrees, those oscillation, okay? You're going to have two oscillations. You have two frequencies of oscillation over here, omega 1 and omega 2. So the system now is oscillating the two displacements, u1, okay, and u2 are oscillating with this frequency, omega 1, and it will have that natural period, okay, tn1, okay? It also can oscillate with, they can oscillate with the second period or the second frequency, okay? So 2 pi divided by w, omega 2 is going to be the second natural frequency. The total oscillation of the building is the summation of the, you have the first period here and the second period, okay? The first frequency and the second frequency, okay? The total motion is the summation of the two modes. So those, we call them the modes of vibration, okay? Now, when you have, if you go through chapter 13, we're not going to do this, but for structures, okay, the most of the, you have to add all the components, okay, of those modes, okay? You're gonna, if you have a 40-story building, you're gonna have 40 modes of vibrations, okay? Omega 1, omega 2, omega 3, and so on until omega 40, okay? But only the lowest frequencies, okay, is gonna contribute the highest to the motion, the amplitude of the motion. So actually, what we did over here, when you had this equation of motion, okay, m u double dot plus ku equals 0, you solve this to find the frequencies, okay, this is called modal analysis. So modal analysis is simply solving this equation to find what are the frequencies, okay, the natural frequencies for the vibration of a given structure. If you have 40-story building, there will be 40 natural frequencies. If you have just a single-story building, you only have one natural frequency, as we did with the single degree of freedom when you had only one story building, okay? So when we have 40-story buildings, we have 40 natural periods. Only the lowest or the smallest, the lowest mode of vibration, the smallest frequency, okay, will contribute, okay, the highest value to the amplitude of motion. So actually, when when we do this modal analysis, we can only extract, okay, or find the lowest frequency, and then base later on, if we want to find the forces that comes on this structure, we can base this only on the lowest mode, okay, the lowest frequency. That will move us, okay, to what is the force, okay, that comes from an earthquake that will be applied on structure, okay? So to understand and find what's the force that comes from an earthquake on a structure, okay, there is a new concept, okay, that we want to introduce. It's called the response spectrum, okay? So what is the response spectrum? Let's take it one step at a time, okay? Let's assume we have this single-story frame. There is an earthquake applied on it, okay, like the one that you had in your assignment, the El Centro, for example. You have this force applied on the structure. You have this ground excitation, so there will be a force of negative m multiplied by the ground acceleration over here. So we have this force applied on the frame over here. The mass is m, the stiffness is k, so you can find omega n, which is square root k over m, okay? So we know the natural frequency here. If we have a multi-story building, we can do the modal analysis as we learned, and we can extract omega n, the lowest omega n, the lowest frequency, because it will contribute the most amplitude of, for the motion of the structure, okay? So we have the structure, we know it's the mass, we know k, we know the zeta, we know omega n, and simply we can find omega d, which is omega n multiplied by square root 1 minus zeta square, or we can simply say that omega n is almost equal to omega d, the damped frequency of vibration, okay? So we have this excitation applied on this structure, okay? Can we find the response? Yes, you can use any numerical method to find the displacement as function of t, as you did in exercise or the first assignment, the second assignment. Any numerical method, like the time-stepping method, okay, or the Duhamel integral, you find the displacement, okay, the response here. So this is the response of that structure with that given m and k and omega n, okay, and zeta, okay. So you find this displacement. Once you find this displacement, we can extract the maximum displacement. So that earthquake will cause a maximum displacement of that value. So with this earthquake applied, the maximum displacement will be that value, okay? I care about the maximum displacement because the maximum displacement means the maximum internal forces, okay? So once I know the maximum displacement, I can find the maximum internal forces that is, you know, in the columns, of the frame, the floor of the frame, and I should design my system or my building to resist that maximum internal forces that is based on this U maximum. I'm not going to design you know, when I design the building to resist this U maximum, it definitely will resist all other smaller displacements, okay? So this U maximum, okay, is the absolute value. I don't care if it's positive or negative, okay? What's the difference between positive or negative? I have this frame, okay? Positive maybe means it's in this direction, okay? Negative means it's in this direction. I don't care, okay, which direction, so it's the absolute value. I don't care about the sign, whether it's positive, so here, this is positive, and then here, this is negative. I'm gonna extract the maximum value, whether it's positive or negative, okay? So this is so important. This maximum displacement is so important. This is what I want to extract. So when I do the numerical analysis to find the response, after finishing, all I need is what's U maximum, okay? Now, let's do the same step, the same earthquake excitation, this same earthquake excitation, but let's assume we have a different structure with different m, with different k, with different zeta, with different omega n. Okay, I want to find the response of that new structure. I'm gonna do the analysis, find u maximum for that new structure, and extract it. Okay, what we're gonna do, we're gonna repeat those steps for different omega n and zeta. Okay, so for each structure, okay, or for different structure with omega n and zeta, you do a dynamic analysis, you extract u maximum. Okay, you have the complete response, you extract the maximum or the amplitude of the maximum displacement, the absolute value of it. Okay, and then you plot this, okay, as function of omega n and z. What do I mean? So you extracted u maximum for different omega n's. So you're going to plot those u maximum as function of omega n's that you did the simulations for, okay, or the analysis for. And then with a constant zeta, let's say for zeta equal 1, and you get this curve. And then you repeat the same with zeta equal 2 and you get another curve. And then you repeat the same with zeta equal 3 and you get another curve. So this is u as function of omega n, the response of your structure as omega n changes. It can be omega n or Tn, and we learned that there is no difference between the two, right? Omega n is or Tn is simply 2 pi divided by omega n. Okay, usually people use the period, not the frequency, okay, to construct those figures. Okay, Tn, the period in seconds, not the frequency over here. Okay, so this plot, okay, is simply called the displacement response spectrum. How much is the displacement or the maximum displacement, okay, that would happen in a structure with a given natural period omega n, or natural period Tn, or natural frequency omega n. Okay, but this is specific to the ground excitation that we simulated. Okay, so this is called the displacement response spectrum. Okay. So in the AISC 7 code, for example, okay, it gives some design response spectrum like those. So it based those on an average, okay, or the maximum, not the average, the maximum of many ground excitation, not just el centro, okay. No, they and they put a factor of safety and they homogenize that curve, okay. So what does this mean? It gives you the maximum displacement that you should design your building to sustain under a design earthquake, not el centro, not any other earthquake, a design earthquake that is larger than all of those, okay, with some factor of safety. Okay. So now, once we now understand what does the displacement response spectrum means, this is the displacement response spectrum, we're going to have another response spectrum that we can construct. It's called the pseudo acceleration response spectrum. Okay, so now once we know this maximum displacement, okay, that comes as function of omega n or Tn, okay, let's ask the question: how much would be the static force, not the dynamic force? Okay, we got the dynamic force from the dynamic analysis, but if we're doing static analysis, not dynamic analysis, what would be the static force, okay, that would cause this displacement u maximum? Simply P equals Ku, right? P equals Ku. So the static force that would give that maximum displacement would be, okay, just K, the stiffness multiplied by that u maximum, okay? Not from the dynamic analysis, okay? So we're asking what would be the static force that is equivalent to that earthquake, okay? The equivalent static force that gives that u, okay? The maximum displacement due to the earthquake, okay? So simply, you know that, omega n is equal to square root k over m, so k is omega n squared m, so I'm just going to remove k over here and replace it with omega n squared multiplied by m. So the static force required to give the same exact maximum amplitude that comes from the earthquake is omega n squared, the natural frequency squared, multiplied by the mass multiplied by u, okay? So m omega n squared u, okay? That's the force, okay? So as you see here, okay, a force that is equal to mass multiplied by this quantity, omega n squared u, okay? Also, you know that Newton's second law says that F is equal to ma. Comparing these two formulas, F equal m multiplied by something, that means that this something is like kind of equivalent. It's not the acceleration, but it's equivalent to an acceleration. We call this a pseudo acceleration. It doesn't mean that the building is vibrating with this acceleration. No, this is not the real acceleration. But this term, omega n squared u, is kind of some acceleration, okay? When you compare this by this formula, this would be an equivalent kind of acceleration, okay? So now I'm gonna, say that this omega n squared u is some pseudo acceleration a, okay? So a is omega n squared u. How much is a, okay? Simply, you just have the u, so you have this displacement response spectrum, okay? Displacement response spectrum. So each of those points is the maximum displacement at a certain omega over here. If you multiply the displacement multiplied by omega n squared, it will give you a, the pseudo acceleration that we're looking for. What's the pseudo acceleration? You multiply the pseudo acceleration by the mass, it will give you the static force that would give you that acceleration, that displacement. Okay? So A definitely here will have units of acceleration, okay? So now instead of plotting the displacement response spectrum, U maximum as function of omega n and zeta, we can plot the pseudo acceleration response spectrum A maximum as function of omega n and z, okay? So simply how to find this, once you find the displacement, you multiply by omega n squared that you use to find this U maximum, and you get that A, and then you plot A as function of omega n for different zetas, okay? And that's what actually the AISC7 gives to you to use to design structures. So simply what you have in the AISC7 figures like this, okay, that tells you, okay, according to exactly where you are in the US, this is the response spectrum that you should use. So based on what's the frequency, you're going to calculate the frequency. If you have a single story building, you're going to calculate the natural frequency of the building as square root k over m. If you have a multi-story building, as we learned, okay, you're going to do a modal analysis, find all the frequencies of vibration, and then pick the smallest vibration or frequency of vibration, and then come over here, find how much is A, and then you're going to multiply this A, okay? You're going to multiply this A by m, to find how much is the equivalent static force, okay, for that earthquake that you should use to design your building. And then you apply this static force on your building and do a static analysis, okay, not a dynamic analysis. And now it is as if you're doing, you changed the dynamic force of the earthquake, okay. You find the equivalent static force of it, and then you just simply do a static analysis. That's how nice those response spectrum are. You construct them by your knowledge in the dynamic analysis, but once you construct them, you don't need any dynamic analysis anymore. You can just extract the value over here and do a simple static analysis as you learn structure analysis 1, structure analysis 2. Usually those A, the pseudo acceleration response spectrum, they call them the response spectrum, okay? They give A over here, the pseudo acceleration. It's an acceleration, so that the unit should be a unit of acceleration. Usually they are given as multiples of G. What's G? G is the gravity acceleration. So I say, you're gonna see here 1, 2, 3. What's 1? 1 is 386 inches per second. What's 2? It's 2 multiplied by G, which is 368 inches per second squared, and so on, okay? So the third assignment that you have, okay, is actually constructing this pseudo acceleration response spectrum for the Il Centro ground acceleration. So simply what will you do? You're going to have get the acceleration or the ground acceleration for the Il Centro earthquake, okay? You're going to get the data of it. You're going to do dynamic analysis, find the displacement, okay? For what's omega n, what's zeta, okay? You're going to do this for different omega n's, okay? You're going to have increments of omega n's. You're just going to start maybe with 0 point, or the frequencies. Let's, instead of using omega n, let's use tn. So tn, okay, well, let's start with, let's say 0.1 second, 0.2 seconds, 0.3, 0.4, and zeta. Let's do this for zeta equal 1%, 2%, and 3%, okay? So actually you're going to be replicating, there is a figure, okay, that gives those pseudo acceleration response spectrum, okay, in the textbook. You're going to be replicating those figures, okay? So you're going to be, doing those analysis, dynamic analysis, numerical analysis for El Centro for multiple WNs. So you're going to be repeating this many times for different WNs, for different zetas, and then you compile them, you extract the maximum displacement from each analysis, and then this you multiply it by omega n squared, okay, you find A, and then that's 1 point, and then you do it again, find another point, third point, fourth point, and then you plot that figure. I hope you understand this concept, okay? If you have any question, please email me. So you have those 3 assignments, okay, that you need to do, and you're going to be submitting your code file that you did to get those figures. I'm going to be sending all of those to you, the assignments and those videos, so you work on them. If you have any question, please email me. We can talk on the phone, or maybe have a Skype meeting, or anything that would help you to do those things. But it's not difficult, and by the way, I encourage you to collaborate together, okay, on those things, so you can work together on this. I have no problem, if you consult with your colleagues, if you need help from them, there is no problem, okay, at all. So good luck and stay safe. Don't go out too much, okay, and stay safe. Thank you a lot, and bye.